piecewise functions, so specifically continuity. Yes. Okay. So this is also just like a little preview of calculus. So we are doing technically calculus right now, and so you'll get a little hint on like what we're gonna like second day of school do next year.
I thought you said calc wasn't a lot of graphs.
No, I didn't. It's got a lot of graphs. It's got a lot of graphs. Not like a ton, but like a lot. Okay, so there are different kinds.
Switching to stats.
There are different kinds of discontinuities. Okay, they're categorized into removable and non-removable. So these are alert new vocab words. Hole. So a hole is removable because you could picture just like plugging in the hole,
yeah,
like removing it pretty easily. So a hole is one type, and it is a removable discontinuity. A hole is yes, we're video.
Oh my god.
A hole is the only type of removable continuity. So sometimes we use these as synonyms. Removable continuity and hole, because a hole is the only type that's removable. My notes are right there.
The
Yes.
whole, I don't know where everyone is. Is the 10th grade gone to?
A-push. There's an A-push field trip.
Yeah.
The 10th grade.
Obviously, seniors graduated.
And then so
It's
Marco
Marco.
and Kat are on A-push, and then Allie's just absent.
I think we're off.
And
Yeah.
10th grade.
No,
So
I was
these
just
are
walking through
so
the
these
hall.
are 10 degrees on a career day. Non-removable discontinuities. These are the three types. A jump discontinuity is this. So here's what a jump looks like. Imagine you're tracing it. How do I continue tracing it? I have to jump. So that's what a jump is it looks kind of like that. So you have like two parts of the graph and they're not meeting up. See how the two graphs meet up? But this one, it doesn't meet up. An asymptote is a kind of discontinuity. You know what those are. And then oscillating, this is crazy. This is a graph of sine of 1 over x. This is the first and last time we'll ever talk about this. But it's like at 0, the y value is everywhere between -1 and 1, but in no particular spot at any given time. So as like, have you heard of like the electron cloud? You know it's within a certain range around the nucleus. It like flies around, but it flies around so fast at any given moment you can't say it's exactly here or exactly here. You know it's going to be flying around.
It's like a fan.
But it's like not, it's just like so fast, it's like bumping up and down, like oscillating back and forth. It's everywhere and nowhere at once. So that's kind of discontinuity. Anyway, that's
Wait,
whatever.
so discontinuity is
Yes.
when there's a separation? Or what?
Yeah, it's like, so continuity is like if you trace it, you don't have to lift up your pencil. So all of these are situations where you would have to lift up your pencil if you were to trace it. Here, you would just go, boop, you know? But here you have to jump. And here you have to lift it up to follow it over. Hello, Miss Montesana. I do have Victoria Anders. Yeah, sure. You have a phone call. Probably just a message. So non-removable jump and asymptote, and we won't talk about oscillating anymore. Right, here is another pretty image. Asymptotes can also be called infinite discontinuities because they go towards infinity. The y value goes towards infinity and behavior. Do you see how are these pictures for you?
Yep. Okay.
I see.
Fabulous.
Fabulous. Okay, let us. Another sheet. There you go.
Okay, you know I
Okay,
had to.
guys.
Okay, listen.
We're getting a new sheet. It's green.
Oh, I look so ugly.
Oh no, Victoria, take the new sheet.
This is the new sheet, guys.
Okay. Okay, great.
Draw. You are not. The camera doesn't like you. You are not.
Okay.
Guys, COVID. Kind
Sorry,
of
guys,
Victoria's
Riley was being
Okay,
a bully.
great. Have a seat. Okay, have a seat. All right. This seems distracting.
Yeah, I kind
But
of.
like, have a seat. It's
Hold on.
cool. We'll just.
Okay.
It's
last
just.
Edits the video to send to the
Okay, so can you look at this?
They just got me.
So we have.
I was focused on that.
Let's look at this.
Focus.
We have continuous here.
Yes.
Look at this. Do you see how this is a continuous function?
Yes.
Yes.
Yeah.
Do we see how this one looks like a hole?
Yes.
Yeah. And then this one's a jump.
Jump.
Jumping.
And then these are 4 different pictures of asymptotes. Yes.
Yeah.
Wait,
There's
so
other-
like
yeah.
1 over x would be.
Have an asymptotic discontinuity.
No, that's it looks like continuous.
Or a discontinuity. Yeah, it's discontinuous. And its discontinuity is called an asymptote.
Wow. I didn't know if it was because you know how that's like one graph. It's not like plot this and plot this. It's like 1 over x makes that.
Makes that whole thing, yeah. So that still counts as a discontinuity. So 1 over x is a good example of a discontinuous graph that's not piecewise.
Good to know.
You know,
Is this gonna be on the quizzer?
this is yes, a
Quiz?
large part of the quizzer on Tuesday.
That has been on the
Oh my
board.
gosh, I have a history test on Tuesday, a quiz on
Wait.
math, a Spanish quiz,
I heard
Tomorrow.
we have 2 half days next week. Is that true?
That's true.
and
Do you know
that
what it is?
SE.
So I actually revised. Remember, I said we were gonna have 4 days of review. We have 3 because there's.
Only reviews are 3 days for final.
So when I fail,
Okay,
that's why.
writing and math. Okay, now we're about to learn some notation. Alert, alert. This is tricky. So let's name everywhere f of x is discontinuous. What about at -2?
Yes.
Correct. What kind of x equals -2? What kind of discontinuity? Raise your hand. Victoria.
Oh,
I'm gonna leave some space here.
X equals negative 1.
What other place? X equals -1. Riley, what kind of discontinuity is it?
A hole as well.
It's also a whole. What else?
Y
Start
equals 1.
Yeah, but we want to give the x value.
Wait, would that be
0.
X
No, but
equals
that would be
0.
a
This
jump,
is a
though.
discontinuity. What kind?
a hole or a jump?
Which one?
Jump.
Jump.
Okay, but this gets where
That's
people
also
confusing.
a hole.
See how it's empty here?
Yeah.
So being empty doesn't count as a hole. What a definition of a hole is the left and the right side are meeting up. Not an empty circle.
Okay, I got you.
Even though like in non-math class you would call that a hole. But in math class we call that just like an empty missing point circle.
Okay.
And a hole is when the left
It
and the right
doesn't
meet up.
include that point.
Correct.
But it's not a hole because it doesn't stop the graph.
X equals
Yes.
3 asymptote.
S equals 3 half.
X equals 3 asymptote.
Yeah.
Okay.
Make sure you're getting this, guys.
Okay, so now here is where it gets tricky. Actually, we'll zoom in a little bit
Here,
here.
I'm gonna give it
Uh-oh. Can you not zoom in on videos?
Not it. You can do it at the beginning of the video.
You can do it at the beginning. Oh,
Did you
I'll let
stop
you-
it?
No, I didn't.
Ew, your tea bag's in it.
Girl, come on.
Here, let me hold it.
It's good. It's good.
There's
It's
only
good.
3 people in class today,
Okay.
guys.
Okay, thank you.
Okay, good.
Story time.
Okay, good.
Actually, I was in here sitting all by myself for like 5 minutes.
It was like 1 minute. Okay, so this is where it gets hard though. Okay.
Why?
So, because I'm going to introduce a new notation. So, do you see how if you were to, the left side and the right side come together? Okay, so
Quadratic.
it's easy. It's kind of like easy to say that in words, but here's the math way to say that. So at -2, there's nothing. But really close to -2. Aren't you like really close to 2 though? Like you're really.
I
Like,
don't know. This graph's kind of wonky right now.
so -2, 2 isn't a point
Why? Oh,
because
a
it's
hole.
empty. But it's like really close to being a point.
Yeah,
You know what I mean?
Almost.
Almost. So that almost is called a limit.
Hmm.
So a limit means very close to. Another new vocab word.
Very.
Are these notes on your website?
What, these specific ones? No, they're not. Okay, so here's how we write it. The limit, we abbreviate it as LIM.
Oh gosh, another abbreviation.
As x
Do you have
gets
to do this?
close
Does it
to,
have to be like that?
Yeah.
what?
Does it have
The
to be
L has to
fancy?
be like that?
It does not, no. You can write a regular L. You can write a regular L, yeah.
Victoria doesn't know how to write first.
Alright.
As x approaches, so the notation for close to is an arrow.
As x approaches -2.
Okay.
-2.
notation for close to.
Yeah, so notation, so this means approaches
It's just the same for end being.
or gets close to. Yes! It's heading towards. Yeah, so we do know that already. Of what function? I gotta name my function. What's my function?
F of x.
Okay.
Are we like?
What are we doing?
equation?
2.
It is 2. Yes. So as you're getting close to -2, the limit is 2. So you're not at 2, but you're really, really close to 2. That's the idea of a limit.
This is
What about the limit? What about, let's just write it right here. The limit as x approaches -2. No, we can just write that. Actually, no, we'll just write that. That's cool. We'll just leave that there. Okay, cool. So that's how you write it for a whole. So can you now, using this notation, write it for as x approaches -1?
So is that like always gonna be the format for it?
Correctamundo. Correctamundo.
Yeah.
You can't really write the f of x underneath. It should be like next to.
Yeah, I just ran out of space. Could you say y
What's
equals?
the y value here? No, because it's not equals. That's the equal 0.
Like f of x is just fancy y.
Yeah, so the limit as x approaches -1 of f of x
Ryan, why do you
equals
have your calculator?
equals what? Victoria?
Homework. It was.
What was it equals?
-1.
It was
Nope.
What are we?
Wait, what did you do for
Oh,
the
0.
answer?
0. Okay, we're gonna get there. I
Okay.
promise. Okay. So how's this? Great. So I would just notice that what they're equal to are always y values. So when I say what's the limit, you're going to give me a y value. So the limit as x approaches -1 is 0. So it's the same as just like, it's the same as like this is a point, only it's an open circle point. That's not really a point.
0's an x and
Okay.
a y.
So let's do a jump, okay? So every hole when it says justify, so the question we just answered was justify your answer using limit notation. This is how you justify that this is a hole. This is on the homework.
So limit is just.
Yeah. And it says like justify why it's a certain discontinuity. That's how you do it. So let's learn how to justify from a jump. If I asked you what the limit is, would you say -1 or 1? Ooh.
Limit is y values, you just said.
Yeah. So both of these are y values though.
But you would say
I said.
-1 because it's
Oh,
limit.
because it's before it jumps.
Good question.
No, I'm really.
Yeah. So Riley, put that away, please.
She's moisturized.
So the answer is both of them are involved. Both the -1 and the 1 are involved. It doesn't have to do with the open or closed circle at all because we're just talking about very close to, not at. So if I were to say f of 0, it would be -1. But I'm not talking about that. I'm talking about close to. So what's the limit as x approaches, the x value is 0, okay, from the left side.
No way.
From the left side. So name me, that's a little minus. Okay, before we do it, this is from, this little minus means from the left side of, in this case, 0.
It's more difficult.
Yeah, it's getting harder. Well, this is the last hard thing, but it's pretty hard.
Hold on.
So, yeah.
No, left side of 0.
Yeah, so what's a number that's really close to 0 and number line-wise to the left of it?
Point
-0.1, let's say.
Point.
.00001.
I said -0.0.
Yeah,
1.
that's good. -0.001.
I just said that.
I said 0.
So let's go to x equals
So
-0.001. So we're right here. Can you find the graph from there? Do you have to go up or down to get to the graph? Down. So the y value is, again, very close to what?
-1.
Here you go. Check.
So on the left, it's -1, and on the
Yeah.
right.
That's
Why does it
correct.
matter though?
Yeah. Well, this is how to justify a jump. Okay, so let's do from the right now. The limit
I used to do it like that.
as x approaches 0. So from the right side, I'm going to put a little plus as a little superscript of f of x equals. So what's the number that's very close to 0 but to the right of it?
Positive.
Point
Wait,
oh.
why'd you put the negative if it's to the right of it?
I put it, that's a plus.
Oh, I can't see.
So left, you go down, right, you go up.
No, not always. Nope.
Why?
Well, left you mean down? Like less than?
But no, like for the limits, like if you do
Do you mean like on the graph or just like
On the
subtracting?
graph.
Not always.
But you know how you went down?
Yeah. I'll show you a counterexample in a second. So like 0.001, right? So I'm right here. How do I get to my graph? Do I go up or down?
Up.
In this case?
One.
So to answer your question, let's say I'm gonna make a new graph. So Lily said to the left is always down, to the right is always up. No. So I could make a graph that's like it's like this and like that. What would the limit to the left of 0 be?
2.
So the left of 0 is here. How do I get to my
Oh,
graph?
it's the way that the graph goes.
Yeah. So you have to like go a little bit to the left of your thingy and then find the graph. In this case, how I find my graph is here. So I'm close to 2.
Oh, okay.
If I go to the right, you know, like at 0.1, and I find my graph, do I go up or down? The
Down.
graph is there,
Because that's where that
which
graph
is close to negative 1.
So you're telling me
Yeah.
that x
Mm-hmm.
limit that is x approaches.
Yep. So limit, yeah, as x approaches 0 from the left.
The left is positive 2,
Yep.
and then it's the opposite. So when it's okay, so it's -1.
Mm-hmm.
Okay.
So the procedure is you say, what's a number a little bit to the left of 0? You find that on the x-axis, and then you find the y value from the graph.
And negative always means left, and plus always means right.
Correct. Correctumundo. Okay, so now let's learn, this is our third type, our third kind of justification. Alrighty. So let's see, I'll start writing in pink. The limit as x approaches, what's my x value I'm talking about now? 3. From the left of f of x equals what? Okay? So let's see it. Let's do it together. Let's do it together. Don't shout it out. I'm going to go a little bit to the left of 3. So here I am at 3. I'm going a little bit to the left of it. Now I need to find my y value. Do I go up or down?
Up.
Up. What's my y value approaching?
Infinity.
Infinity.
Wow.
Mm-hmm.
This is a lot of weird.
Yeah.
So it's going to the left. It's going infinity.
So, and then.
So now let's see to the right. So limit as x approaches 3 from the right, tiny little plus sign of f of x.
We're waiting for sure.
Don't write the answer yet, just like let's practice writing the limit notation.
I'm writing it.
So what's the number a little bit to the right of 3? Right here. 3.1.
3.0.
0 or 1. Great. And then I need to find my y value. So I go negative infinity. Okay. So here's why the left and the right thing. So the whole, I could actually also write my whole as the limit from the left and the limit from the right are equal, and they both equal 2. So take a look at this green sheet. All of this is summarized on here. So can you see just read all these like limit guys here, all these little justification statements. Just take a sec to stare at them. Lily, you reading them?
Yeah. Which ones? Limitations. Oh,
I don't understand.
Okay, so the continuous, the limit from the left.
the
Yeah, the continuous one is confusing. Yeah, okay. Maybe because we didn't really learn it yet.
we just learned it.
We didn't do a continuous example. Okay, let's do the continuous example. Okay, so right here. So the limit, okay.
This one I know.
I'm just doing the green sheet here. So the limit as x approaches 0 from the left. What is the limit as x approaches 0 from the left here? So I go a little to the left. No.
2 pi.
Oh. The y value here is 0. Yeah. So this would be 0, yes?
Yes.
What about from the right? 0 from the right.
Yeah.
It's also 0. Can you see how it's like from the right it's also 0? And then what is the actual y value? What is f of 0? 0. So that's a continuous function. So the definition of continuity, this is a very, very formal definition of continuity. So we're now getting more advanced than like tracing your pencil. So the definition of continuity is the limit from the left is the same as the limit from the right, which is the same as the y value f of that point.
So this is all y axis.
Yeah. Every single, yep.
Okay.
So the limit, so that's continuity. The limit from the left is the same as the limit from the right, is the same as the y value. Okay, you want to keep reading it?
So is there
Okay, so
only different way to do this is if
Yeah.
you move it over
Okay,
to
yeah, I
2
don't
or
like the
something.
like formula.
yeah,
It's like kind of
it
makes
is
you have to think.
it is yes, I agree. And so if you look at the whole one, see how the whole one looks like this, you know?
Would it all be equal?
So the limit from the left is the same as the limit from the right. So see how I wrote that on the paper?
Yeah.
Like these two are just like equal to each other. But what about the y value? Is it equal to the y value? The actual y value? No. So not equal to f of 0.
Because of the
Can we
Exactly.
do it like how we did on this, or do we have to write it?
You could do it, yeah. So actually, can you, on the whole, can you change this a little bit? So you don't need to do the left and the right. So can you also write this on the whole? So this, you could also write limit as x approaches 0 of f of x with no plus and minus. The limit would be 0 here, but is not equal to the y value. Like f of 0, which is like 4 or 5 or something, 5. So you can also write it like that.
So it's 2 0, but it's not.
Can I just
Mhm.
write it like?
Or does not equal 5, you mean? Like that? Sorry.
Wouldn't it just be 0?
The limit, okay, so you could say the limit equals 0, but f of 0 is
Are you gonna
5,
put this on
and those are
Elastic?
not equal. What?
Are you gonna put this on Elastic?
Do you want me to?
Well, I'm here for class.
Yeah, maybe. I'm thinking about it. Thinking about it
With questions.
with questions for them to do.
Mhm.
Wait, is this, Riley, what's your question?
I know, just like how we did it on the classwork, all we
Yes.
did was just like equal 0. Like, is that not good enough? Like, do we have to include the f of 0?
I would like you to include this.
Okay.
Because having a limit, like you could be continuous. So like let's say I didn't include this, right? Let's say I didn't include this. This could be the graph, just like a straight up continuous graph.
Okay, yeah.
So you need to specify that like at the point it's empty. Because that's how you get a hole. So you would need to say that like this is not equal f of 0, which is 5. Okay.
Okay.
Okay, do you want to look at the jumpy thing on your paper? See if that makes sense.
That is not equal to that.
Riley, what did you learn tonight?
It's not time for closing it. We have another like 30 seconds before closing.
Limit of x
So-
to 0 to the negative.
So the left side is not equal to right side.
Right, the left side is not equal to the right side. What is the limit from the left of this thing?
F of x.
0.
Yeah. It would be 0. What is the limit from the right?
2.
Do we agree? It's the limit from the right.
2.
So from the left, she says it's 0. I agree with that.
Oh.
What about from the right? She says it's 2. So see how they're not equal?
Oh.
So that's the justification for a jump.
That is a joke.
Mm-hmm.
But it's gonna be the same for all.
The whole, the limit from the left is equal to the limit from the right. In other words, they meet up, the left and the right
But
side.
you didn't say not equal to when we did it just now on here.
Oh, yeah.
But it would be not equal to.
It would be not equal to the y value, yeah. So, but that's not equal to f of whatever, yeah. All right, you want to tell to each other about what you learned? It's a lot.
We learned a lot today.
We learned a lot today.
Yeah.
I learned about holes.